and welcome to the final office hours of week 6. I want to know, as always, do you have any questions? Good morning. What is going down? Oh, I have not. I haven't seen it yet. Here, let me pop open my inbox. Or inboxes, I guess I should say. All right, here we go. Couple questions on the homework for Chem 124. All right, let's see. Here, I'm opening it up. Okay. So let's see, 1A. Let's see, I believe there's no reaction because there's no ether located on the molecule. Yes, it can't be a Claisen. Okay. So you're spot on. You're spot on with your assessment that there's no, there's definitely, okay, so here, hang on. Let me stick this right here, this right here. Okay. So looking at, this molecule, and then there's just heat. And the question is the reaction, what are the products? It says provide the products or reagents for the following reactions, stereochemistry where necessary. Some reactions may require more than one step. All right, so Nathaniel, you were spot on when you say there's no Claisen here. Like that is 100% correct. Because yeah, you need that ether to make the Claisen work. That's not going to go down here. Excuse me. Now, there is no Claisen, but there is a possibility for Diels-Alder. Diels-Alder is a reaction between a diene and a dienophile, where and these are only go with heat. Where we make 2 new sigma bonds. And then a new pi bond right here between, if we number these carbons 1, 2, 3, and 4. There's a new pi bond between 2 and 3, and then sigmas between 1 and 4 to the, if we number these 5 and 6, carbons in the Dienophile. Now, you may be wondering why do I put a question mark here? The only reason why I'm putting a question mark there is I'm not sure if a Diels-Alder will happen because of steric strain. This substance might be, yeah, dienes and dienophiles can totally be on the same compound. Those are called intramolecular Diels-Alders. And actually they happen faster than normal Diels-Alders because since they're both tethered together, it's easier for them to find each other in space. So intramolecular Diels-Alders, totally a thing that can happen. The reason why I'm not sure if this Diels-Alder will happen is because I'm not sure if the product might be too strained, and I'll show you what I mean. Let me just move this to a different layer. All right, so let's look theoretically at what our product would be if a Diels-Alder goes down here. So this would be there we go. Carbons 1, 2, 3, and 4. And this would be carbons 5 and 6. That would form the ring. And if you look at it, so I'm going to redraw this. To look like our usual Diels-Alder. So here's the weird thing. So when you look at what would go down if a Diels-Alder happens, we'd make a new bond between what I've numbered 4 and 5. So we'd have a new bond there. A new bond between 1 and 6. So 1, 2, 3, 4, 5, 6. There'd be a new double bond between 2 and 3. But the thing is, 5 and 4 are still there. If you look at it, and I'm going to switch up my method here. I'm going to call this A, B, and C. We still have carbon A, which is bonded to both 5 and 4, B and C. So this is carbon A, still bonded to 5 and 4, B and C. So I don't know what the steric strain is for like this kind of dicyclopropane system is. I know cyclopropane by itself is super strained. This might be too strained. So I'm going to put too strained to form. That's what I would honestly, I would ask your lecture instructor. I don't know if they're like doing that level of analysis or if they expect that level of analysis from you. Just from my perspective looking at it, I'm not sure that this molecule would be able to squeeze into place to form that bicycled cyclopropane system. Maybe it could, but I don't know if that's a thing that if they've talked about considering steric strain as to whether or not something will form with you guys or not, or if they just want you to recognize dying dienophile, click it together. So that's something that I would check with your lecture instructor. With this first problem, what I can definitely say is you're spot on. There's no Claisen. There's the potential for a Diels-Alder because you have a Diene and Dienophile, but I don't know if the product is too straight. Does that make sense? Okay, solid. So it's probably just wanting to see, can you recognize Diene together with Dienophile? Cyclopropanes with specifically what are known as vinyl cyclopropanes. So I know that these... Oh, wait a minute. I was like, I know these rearrange with acids. Hang on. There may be one other thing this can do. Just give me 1 second here. Okay, hang on. All right, Nathaniel, there may be one other thing at play here. Sorry, it's my brain is still waking up, and I just... So I guess my question, sorry, is has she talked about the rearrangement of vinyl cyclopropanes? Because there is one more thing that could go down here. So, just for the sake of being, not yet, okay. Just be aware that this is a reaction that happens. You see how you have a vinyl cyclopropane? Actually, there's two ways this can rearrange. Okay. I'm going to write this here just so you're aware of it. But it would actually be pretty complex because you'll see after I do this first one, there's two ways this thing can rearrange. These structures undergo a radical rearrangement. So I'm going to just number this. 1, 2, 3, 4, 5. So this can undergo a radical rearrangement to release the strain of the cyclopropane. So it forms, we've got a radical on the carbon I've numbered 3 and the carbon I've numbered 4. Now this is reversible. It can blip open back and forth, back and forth. So this is 5, 4, 3, 2, 1. But part of the reason why this happens is because that radical on number 3 is stabilized through resonance. So we can draw a resonance structure. And you'll notice I'm using resonance arrows, not equilibrium arrows here. To put the double bond between 2 and 3. And then we've got the radical, each radical on the 2 terminal carbons. Now these can recombine in an irreversible step to make a cyclopentane, where this is 1, 2, 3, 4, 5, and that last bond that we made, that last step, forms a sigma bond between 1 and 5. So I don't know, whenever I see a vinyl cyclopropane, like we have in this structure, I wonder if we're looking at a possible rearrangement, kind of in this style. If we were, that would open us up to all sorts of possibilities. Okay. All right, I'll move on to your next question. It's a weird one. It's super cool, but let's move on. Okay. So your next question was about 1B. All right, you believe your dyeing reactant is correct, but a little unsure about the placement of the carbonyl functional groups on the alkyne. Their placement doesn't really matter since it's located on the alkyne. Okay, so here, let me take a look. Okay, at B. All right. Oh, okay. And this is what Diene and Dienophile do you need to prepare each of the following. Okay. So here. So this is the Diene that we're talking about. We've got a couple aldehydes hanging off. All right, and so your assessment is spot on. Whenever you see these fused ring systems, you know that your diene was a cyclohexadiene. 1, 2, 3, 4, 5, and 6. So that's spot on. Your diene was indeed a cyclohexadiene, and you astutely noticed that for your dienophile, you have a pi bond, a carbon-carbon pi bond between carbons 2 and carbons 3. So the only time you have a double bond there is when your dienophile was an alkyne. And so this would be carbons 1, 2, 3, and 4. Where between 2 and 3 you have a pi bond left over because we had 2 to start with. One of the pi bonds gets sacrificed to the Diels-Alder reaction, but the other one remains. And also, Nathaniel, I think your question's super astute because you were asking about endo versus exo, and you know with the electronic withdrawing groups that those like to go endo for the Diels-Alder. Totally true. But something to note is endo and exo only apply for alkene dienophiles. Because you have an alkyne, there is no endo or exo. And the reason for that is the alkyne is just a straight line, right? So with an alkene, it's kind of bent like this. So is it going to slip under, or is it endo, or is it going to be pointing out exo? But for an alkyne, because it's just a straight line, there is no endo or exo. It just lines up and then cyclizes. Also, your answer is totally correct. It's spot on here. Totally. The nice thing about the alkyne dienophiles is you get a free pass with the endo and exo stuff, you don't have to remember which way is it going to go because it just clicks into place. It's a straight line. Dude, also thanks for bringing OChem to office hours. This is literally my favorite stuff to talk about. So it's always a treat when I get to do some organic chemistry in the morning. Yeah, yeah. All right, let's see. Oh. Oh. Okay, here I'm pulling it up. Yeah. Oh. Okay. Excellent question. Okay, so I see. So it says determine which of the following compounds are aromatic or anti-aromatic. Show all calculations to receive credit. Yeah, totally. The one with nitrogen and sulfur. So So we're wondering if this is aromatic or anti-aromatic. Anti-aromatic is has 2 pi electrons, right? It falls into that pattern, whereas aromatic is, or sorry, not 2, 4. Where aromatic is 4 pi plus 2. Okay, and the question with this structure is so this structure is, let me draw it up real quick. And sulfur's here. The question is this aromatic or anti-aromatic? And really where the question lies is we have 3 lone pairs in this molecule. And the real question, the way we're going to answer this, is are any of these lone pairs in p orbitals? Yeah. Nathaniel, that is correct. Because here's the thing. When you look at both of these atoms, right? Because this is the real question is, are any of these lone pairs in p orbitals? One way to look at this problem is you could take a hybridization approach. This nitrogen is sp2 hybridized, right? But this lone pair right here, so sp2 hybridized means that you have 3 sp2 orbitals, right? And 1 unhybridized p orbital. Now here, the 1 unhybridized p orbital is being used to make this pi bond. So that p orbital is in use for the pi bond, which means that this lone pair is just in an sp2 orbital. And to contribute to either aromaticity or anti-aromaticity, your electrons have to be in a p orbital. Otherwise, they're not part of the aromatic or anti-aromatic system. All right, so that's the analysis there on nitrogen. When we look at sulfur, so we can get resonance in the mix, right? We can bounce these lone pairs down, which pop those electrons out. and we get a resonance structure where we have a pi bond and one lone pair on sulfur, and then two lone pairs on nitrogen. In this resonance structure, sulfur has a formal charge of +1, nitrogen has a formal charge of -1. But clearly, this resonance structure tells us something. Because these lone pairs, one of the lone pairs on sulfur, can be used to make a pi bond in a resonance structure, that tells you that these are in a p orbital, which means they count towards our electron count for aromatic or anti-aromatic. When you look at the other lone pair on sulfur, it's less easy to see in the first resonance structure, but more clear in the second resonance structure. This sulfur is sp2 hybridized. The second lone pair is held in an sp2 hybrid orbital because the 1p orbital is occupied in this instance. It's occupied by the other lone pair. So, all that to say is your sp2 orbital, if a lone pair is in an sp2 hybrid orbital, it's not going to contribute to the number of electrons in the aromatic or anti-aromatic system. If a lone pair is in an unhybridized p orbital, it will contribute. So for nitrogen, its one lone pair in the first resonance structure does not contribute because the p orbital is occupied to make that pi bond. For sulfur, one of its lone pairs does engage in resonance and so is in that unhybridized p orbital, but the other lone pair is not. So when it comes to counting how many electrons do we have for our aromatic or anti-aromatic system, we have 2 plus 2 plus 2. So a total of 6 pi electrons, which fits 4n plus 2 aromatic. Dude, I'm so glad. I'm glad that helped it make sense. Whenever I'm doing like aromatic versus anti-aromatic stuff, I find it really helpful to go back to the basic hybridization of each atom, because p electrons contribute, the sp2 or sp hybrid electrons can't. So it kind of simplifies the problem. And dude, once again, thanks for bringing organic chemistry to the early morning office hours party. It is my absolute favorite thing to talk about, and I rarely get to. I'm mostly teaching Gen Chem these days, so so this is is a treat beyond description for a chemistry nerd. Okay, yeah, here, let me pull that up. Okay, yes, totally. Okay, letter E, second page. I was wondering if my numbering of the carbons was correct, or if it matters in this problem. Ah. Okay. Here, let's take a look. So we have all right, so your number's spot on. Um, it's definitely a 1-2 addition. Um, but here's the thing. So there's actually, when you look at it, the first step is definitely going to be protonation of an alkene by the strong acid. The question is, where does it land? And so if you use that first alkene to protonate, you get what is a great carbocation. It's tertiary and it's resonance stabilized, right? You get the benefit of a second resonance structure, which helps stabilize, which adds to the carbocation stability. Resonance structures are always add to the stability of a carbocation. Yeah, Nathaniel, you totally got it. If you look at what would happen if you protonated with this alkene, we still get a tertiary carbocation, but we get one with a lot more resonance structures. Right, we get one from the other alkene, just like above. But we also get a boatload of resonance structures from the benzene ring. All right, and I'm sure I don't need to finish drawing the rest of them. You know the drill. It moves around the whole benzene ring. And so the point is, this carbocation is far more stable. And so the 1-2 addition product that you're going to see is this one. Where as you numbered them in your structure, 1, 2, 3, and 4, the bromine will go to number 3, and the H will go to number 4. And the reason why we add bromine to carbon number 3 is because that is the most stable carbocation that can form in this molecule. Dude, totally, totally. Dude, you too. Thanks for adding some organic chemistry to my morning. It's been a blast. All right, and that does it for office hours this morning. It was a very organic office hours, which is fun. Anyways, I will catch you all on Monday, and hope